All right, now we're going to talk about Hess Law, which is going to give us, help us determine the energy change during a chemical reaction. Okay, so just a little recap. So when we have heating and cooling, we're going to use specific heat, or Q equal MC delta T, to get the energy involved. If we have a phase change, we're going to use the either heat of fusion or heat of vaporization, depending on which way we're going. And then now we're going to do chemical reactions, and we are going to use Hess Law. Okay, all right, so basically Hess Law just says that regardless of however you get to the final product, no matter if you are using a catalyst or whatever, it's independent of the path. The energy change is going to be the same. So this picture, I think, is a little better. So the blue line is representing a multi-step mechanism. So you have two activation energies, you have two intermediates here. And so this is a two-step mechanism. Or you have path A, which is, we'll call it a catalyst mechanism. So it has a different activation energy, but irregardless, the energy of the reactants and products are the same. So the difference between them will always be the same. So that's what Hess's law is saying. No matter what way you go about going from reactants to products, whether it's a very quick method via catalyst or a mechanism where you have to do several steps that takes a long time, the energy change between the two is the same. So it's kind of like displacement in physics. All right, so let's just go ahead and look. All right, so often you're given formation equations. Formation equations are basically synthesis equations where you get just one product, and it tells you the energy that is lost or gained during that reaction. Okay, so what we're going to try to do is use these three reactions to determine the energy change for that reaction. Okay, so essentially we're trying to recreate this reaction by combining all of these. All right, so I'm going to start with CH4 first. All right, CH4, here it is in our formation equations, but here it's in the reactants and here it's in the products, so that's kind of an issue. So what we can do is we can just flip that formation equation around so that the thing that we wanted, the CH4, is now part of the reactants, okay? But when we flip that, we need to flip the sign of our delta H. So now we have positive 74.8 at that place, okay? So we've got our CH4. Now, diatomics. Diatomics, so anybody, any of the 7 special diatomics, H, NO, F, Cl, Br, I, are going to have a delta H of formation of 0. So essentially, you don't have to worry about them when you're trying to do this equation. All right, so now we can move on to the CO2. There's CO2. It's in the products of that and the products here, so there's no need to flip it. So I can just write the equation as is. And the value is not going to change because my equation didn't change. Okay, so we got CO2. Now we're going to work with the H2O. So here we have our H2O. It's on the products and products, so I don't need to flip it either. So I can just write it down. Okay. Now, if you look, I only have one H2O here, but it says I need 2 to make this equation. So I need to multiply my whole equation by 2 so that I get the correct number of H2Os. Because I multiplied my whole equation by 2, I also need to multiply my delta H by 2. Okay? So now that we have, or we think we have, got all of these things made, we're going to try to cancel things that are on the opposite sides of the equation and then add these equations up to hopefully make this first equation again. Okay? So I got carbon on the reactants, carbon on the products, got a 2H2 and a 2H2, and that looks like all. So now I just need to add them up. So on the reactants, I got CH4, all right, and then I got 1, and then 2 over 2 is 1, so 1 plus 2 is 2O2. And on the products, I've got CO2 and 2 H2O. Okay? So when I compare that back to my original equation, I see that I have made my original equation, which is good. So this is like a great way to check yourself. Now that you've done that, all you need to do is add up all of these values. So when we add up all of these values, we get that. So that is the delta H of combustion for CH4. Okay, so negative 890.36 kilojoules. Okay, so you're making the equations, you're swapping them around, and basically you're trying to use the equations you're given to make the initial equation. Okay, now there's a shortcut, of course. So if you are not giving equations and you're just given values, you can use the shortcut. You can also use the shortcut with the equations, but when you have the equations, it's great to be able to check yourself. So the shortcut is going to be the sum of the delta H of the products minus the sum of the delta H of the reactants. Okay, so basically what we're going to be doing, let's go ahead and get my page a little bit bigger there. All right, so I'm going to start on this side. So I've got 2 H2O's, and H2O's value is negative 285.83. And I've got 1 CO2, and CO2's value is negative 393.5. All right, so that's all the products. So I need to get all that and add it up to get the sum of my products. And then we're going to subtract the sum of the reactants. Well, O is 0, so I don't have to worry about that one. And then CH4 is negative 74.8. Okay, and that's going to give us our answer once we work it all out. Okay, so when we start plugging in our numbers and getting our values over here, we will get this plus negative 393.5 plus 74.8. Okay, now we're just going to plug all those in, and you get, amazingly, the same exact thing when you added the equations together. Okay, so it gives you the same exact thing. It's just two different ways to go about trying to solve the problem. All right, now we got one more example. Okay, so it says that the delta H for the combustion of ethene, as shown by this equation, is negative 1411. Wants us to find the delta H of formation for the ethene. Okay, so we're not given that. So now we're trying to solve for something in the middle. We could add the equations, or we could do products minus reactants. Products minus reactants is a little quicker, so that's the method I'm going to choose. So we've got 2 H2O's, so I'm going to do 2 times H2O's formation value, and that is added to 2 CO2's, so there's our CO2 value. All right, so those are all products. And then remember, we don't have to worry about O, and we don't know C2H4, so we're going to minus that, and that's going to be our X, and this is all equal to negative 1411. All right, so when you start working out this side, you get this. Okay, and then simplification here. All right, and then we're going to get it on the correct side. So we're going to add the 1358.66 to the other side, and that is going to give us negative 52.34, which is equal to negative X. Then you're going to inverse your signs to get a positive X. So the energy for C2H4 is 52.34 kilojoules.